Good evening, everyone. It's my pleasure to have today Professor Terrance Boult here with us in this series of talks for the Artificial Intelligence Lab, Recode AI, at the Institute of Computing, University of Campinas, Brazil. Terry is a very good friend of mine, my co-advisor during my PhD when I visited him at the University of Colorado at Colorado Springs, and he is the culprit for many of the things that I push you to do every day. I learned a lot from Terry, and I continue to learn always when we talk. And today he is going to talk to us about the unified framework for theories of novelties, Openset and open world recognition systems. Terry is the Pomar Endowed Professor of Innovation and Security at the University of Colorado, Colorado Springs, and also the co-founder and CTO of Securics Inc. He is an established international expert on computer vision, biometrics, and cybersecurity, member of the IEEE Golden Core, and has been an IEEE Distinguished Lecturer. And also in 2017, he was elected an IEEE Fellow. Terry is the founder and the primary architect and co-director of several of the UCCS Bachelor of Innovation family of degrees, and an inventor and serial entrepreneur that has been involved with multiple startup companies and with widely deployed software and technology government contracts. So Terry, once again, thank you very much to take your time to talk to us today. This stage is all yours, and it's always a pleasure to have you here.
Well, thank you, Anderson. It's great to chat with you again, catching up a little bit. So I'm going to go ahead and start my talk. If I'm going too fast and you're in the audience, please just tell me to slow down. Right? I timed this so I can do it, but I have a tendency to go faster as I get excited, and I get excited about my work. So this is actually a combination of two different aspects of our work. So the first title here, and you'll see all those authors, we had a paper last year at AAAI towards a unifying framework for formal theories of novelty. I'm going to start with some of that work, and then I'll talk about how we're using that and how it relates to our work on Openset and open world recognition systems. And before I get too far, I want to mention I have two postdoc openings, one in open world recognition and another in face recognition. And there's a URL there. So if you know somebody who is looking for a postdoc position, please have them contact me, have them go here, and we'll move forward, see where we can go. So this actually came about because, come on, gotta get in the right window. I'm actually part of a large DARPA, which is a Defense Advanced Research Projects Agency project in the US. And our project is joint with Kitware and Walter at Notre Dame. And it's on what we call formalized learning for open worlds. And the idea of our overall project is centered around extreme value theory and applying it in open world learning in a whole bunch of approaches. And I'm not going to go through all the detail of this slide. But it's a very big team. We're doing lots of things. We're looking at image domains, text documents, video, a whole bunch of different things, looking at how we convert them into representations we can apply extreme value theory to. As part of that, we were actually challenged by DARPA as us. There's actually people from about 20 different universities and companies working on this. As we looked at it, the increasing interest in research of Openset and open world, as well as out of distribution detection, novelty detection. There's all these things that people are finally starting to look at, but we really lacked a good theory or even a formal definition of what we mean by novelty. All of the authors of our paper, right, and you saw that long list, right? They're all part of this Ceylon project from DARPA, working across multiple domains. So here we are, leading AI researchers across all these different groups, and we didn't even have a consistent interpretation of what is novelty. And we've been working at this for 2.5 years, and we still don't have complete agreement. We now have slightly more than half of the groups that are sort of converged towards our definition of novelty, but other people don't go along with this definition. I'll come back to that when we get a little farther along. So we started off with a very fundamental question. What does it mean for something to be novel? If I want to say it's out of set, I want to say it's novel, exactly what does that mean, and how do we formalize that? At one level, everything is always changing. So novel is not just different, right? Literally the Earth is moving through the solar system, right? We're never in the same place twice. Everything is changing. So we have to have something a little bit more subtle. And what do we mean? Do we mean a novel state of an object, a novel instant of an object, a novel class, a novel color? All of these things have to be looked at and try to decide which of these do we really mean. And the answer is we can mean any of them. So our goals were really to look at how do we define, or how do we develop a framework and theories that formalize novelty in a domain and make usable predictions about detection and learning from those novelties. So we wanted a framework. Novelty will be domain dependent, but our framework, we wanted to be general enough that it does not require knowledge of a particular domain to formalize it, but it does to define the framework, but it does to formalize novelty for that domain. So we wanted a framework that can be applied in different domains, in supporting both what I will call closed worlds, generative synthetic worlds, as well as problems that can only sample the world. And those of you who work in Edison's lab, you're probably doing a lot of vision related stuff. Vision problems, we can only sample our world. We can't assume we have a closed model of the world and simulate it. But people who are working on lots of AI problems, something like VizDoom or CartPole, right? They have a simulator and they can simulate the entire world. And so as they go through that process, then we want to be able to say, I can talk about novelty in either one of those. So the insights we developed as we worked through this is a team of multidisciplinary researchers. Now we'll be very careful. This first part, although Walter and I were sort of driving forces, it was a very interdisciplinary group and we learned a lot from each other. One of the first things was that, of course, what's novel depends on the tasks, the world model, the agent's perception and sensing, and of course, the agent's experience. And you have to consider all of those. We worked towards a model that had to say, we're going to make these things first order objects that we can talk about. And that different tasks, different world models will have different theories of novelty. If I'm looking at somebody who I've seen before from a face recognition point of view, the person may not be novel. But if today's the first time they've ever had pink hair, then at a different level, they're novel because their hair is novel. Both of those can be, or I could say, I only care about identity, that person's not novel. What I want to do, the task, is it a general identity task, or is it, I'm looking for what's different about this person? Two different tasks, same exact image, two different outcomes for what's novel and not. So we have to think about how we're going to work that into our framework. Come on, mouse. Oops. So we developed this high-level framework, and I'm going to take a little while to go over this slide because at a core, it's important that we sort of see these different elements. So as I said, novelty depends on the world. So we have some representation of world space, and to keep it relatively simple, we're going to assume that that's a vector in R to the D for some dimensionality. And if you wanted to use graph representations, then all we do is assume that the graph has a maximum dimensionality in terms of nodes and arcs, and then we can still talk about a world state in this representation. But it's not just what's in the world. Novelty, in my view, begins in the world, but I have to actually have what we call the observed space. Given what's in the world, we go through some perceptual operator to develop this observed space, which we also represent as a vector, this time in R to the D instead of R to the D prime. So we observe something. In the case of images, this would be we observe an image. And then finally, and when we talk about an agent, a software system, an agent, a robot, whatever you want to think of it, right? We just call them generally agents. The agent actually lives in some state space. It goes through a sequence of internal states with some state recognition function that goes from the perceived observed space to decide whether or not it wants to change its state function. And then the agent can have actions. The actions can adjust its state. The actions can go back and change the world. If it's a robot, it could go and push an object or do something in the world. So the world state may be affected by what the agent thinks the world is. So all of this is going on in the world observed by the agent. Along the way, as the agent does this, whatever we go through this perceptual operator, we can make a copy of that and put in what we call our experience tensor. And this is going to allow us to get into defining what we really mean by dissimilarity. So to define the many types of novelty that we're going to go through, we're going to actually have these multiple operators. So the first and most fundamental of these is the dissimilarity operator. Given two world states, I'm going to be able to say this state is different from that state. And this is critical and also flexible. We're not saying how to define dissimilarity. So dissimilarity could be pixel-wise L2 distance, or it could be L2 distance between the outputs of the feature representations of a ResNet 50. Or it could be, ResNet 50 has to be in the observed dissimilarity operator. So in the world, I could be saying, what's the difference in the labels? Is it the same person or not? Observe, they could take two images of the person and say, now what's my dissimilarity? Is it the pixels different? Is their identity in a ArcNet, arc face representation different? ResNet 50 different? Okay. And then there's an agent dissimilarity operator, which allows us to say the agent representations are different. You'll notice both the observed dissimilarity operator and the agents live in the world space, even though I've called them observed and dissimilarity. We actually require that eventually the observed dissimilarity operator reduces from the world space down to the perceived space. But the reason we left it in world space was because of the very general problem, the observation might be a function of the camera, which may or may not be something that the agent has direct control over. So this operator might be something that changes as the agent changes the world or moves its position around. So we left these in a very general state. So this gives us dissimilarity. And this is the fundamental difference. We're going to end up saying we can look at how dissimilar things are with respect to our experience and say, now the last row here are what we call the regret functions. And regret functions are very common in machine learning, especially RL type. But here we make them in a very general sense. What we really say is, given the world and some action, there is some regret I have for having taken that action. This may or may not, in general, the world regret function is not something that an RL agent could get because they can't compute it. It lives only with an oracle. The same is true with the observed regret. An oracle will say, if you made that choice. So if I added an oracle, I could get there. The agent's regret function is something the agent may or may not be able to compute, but at least you begin to have that sense. So here, and you'll see why in a second, we talk about these regret functions. Because although I can say that something is novel regret, the different types of novelties will end up using it. So given these 6 core definitions now in our paper, we can then go into the very different types of novelties. And I see I have an error in that slide. I'm going to go fix it for a second. I fixed it in the other version, but forgot about it here. Forgot to save it when I made that update. So we actually talk about 3 major types of novelty: world novelty, observed novelty, and agent novelty. Just like I had dissimilarities for world, observed, and agent. And world dissimilarity is actually very simple. We're going to take over our experience tensor, all the things we've experienced, and we're going to look for all the states that are in there. And given some new state, we say this new state W hat is novel if the dissimilarity between it and everything in our experience tensor is greater than some threshold delta W. And similarly, when we look at what's going to go on for observed novelty, we're going to do something similar, except that we're going to use the observed dissimilarity, not the world dissimilarity. So these two are very straightforward. They're basically saying, I'm going to take this dissimilarity operator, look over everything I've experienced, and now threshold it. And then given that threshold, I can say that this is or is not novel. Obviously, it depends on the thresholds. It depends on the dissimilarity operator. The framework doesn't say how to define either of those. That's up to you for your problem. The last one is agent novelty. And we consider something to be agent novelty if the agent has a state, a set of states for whatever it calls novel. So in an Openset recognition algorithm, if I say unknown, then I'm saying it's novel. Now, I might be wrong in doing that. So we'll have to talk about how those things interact. But agent novelty is the agent actually saying it's novel. And one of the reasons we considered all these very different settings is because things can be novel in the world and the agent can get it wrong, think it's not novel. Or it might not be novel in the world, but the agent has a bad representation and says it's novel. And maybe that's because the agent has not found a good way to represent things. So we'll have to go through them. But now let me get back to the regret and why this became an important part of our conversation. So dissimilarity and regret tie together for us to define a few other types of novelty. And in that drawing, I forgot. So in this drawing, we have imperceptible novelty. I'll come back to that. Unanimous, ignored. These are just some. We actually, in the paper, we have a whole lot more. And in the newer version of the paper, which is not yet published, we're going to put it on our archive soon, we have an even more detailed analysis of different things. But we can look at the different types of novelty, which I just defined. So something that is a world novelty, an observed novelty, and the agent novelty says it's novel. We call this unanimous novelty. but I might still have regret, right? Just because everyone said it's novel doesn't mean the agent made the right choice and actions. Or I could have no regret. You'll notice we have two kinds of regret. We have world regret and perceptual regret or observable regret. When those two disagree, we have a problem. Because if I'm looking at it from an experimental point of view, one of them is saying, in one case, I got it right, there's no regret. And the other case, I'm saying I got it wrong. And either one of those causes us problems because we call them nuisances, because from an experimental point of view, you're sort of saying you have two different measures and you're going to get them wrong. And I'll go through an example of that in just a second. But you can sort of see this table allows us to talk about other kinds of things. Another one that's very important in our work is imperceptible. This is something where the world says it's novel, but from an observation point of view, it's not. Right? So this might be something where even though it has changed, maybe it's too far away, and when rendered into the camera, it's just too small. I can't see it. So it might be an imperceptible thing. Obviously, that causes lots of problems for data-based recognition systems. And then I can have these things we call faux novelties, which are when it really isn't a novelty, but the agent starts saying it is. And this is when I say something is known and it's not, right? These are not real novelties, but they're being declared by the system to be novelties. And one of the reasons this taxonomy was useful is that it gave our teams a lot more nuanced ways of talking about the various things that can go wrong. We talk about Openset recognition. But to give some examples of difficulties and nuances, I want everyone in the audience to sort of think of how would you label each of these images? These are actually all three examples from ImageNet, and you have to give it a label. So think about it for a second. And now let's see how well you did. So here are the official labels. The first one is a cherry. There's a bunch of cherries here in front of the dog. When I polled my lab a couple of times about this and some undergrads, right, almost everyone went for dog and not for cherry. This one is a gamma, right? And some people went for the truck. Lots of people just called it a lizard, but its proper name is a gamma. And then this one over here is a person. Despite the fact that the canoe is by far the biggest object in the scene, this is a person. And so we get into this problem that using a single label for complex worlds can lead to a particular type of nuisance novelty. If we disregard the best label, the regret measure is going to be flawed. So in a sense, if I use top one and you have to get these right, you are in trouble. For some of them, if I use top five, then you'll get them right and then they'll be okay. So this talks a little bit about how I measure that dissimilarity in world space and regret in world space, sort of feedback into our system design and our experimental design. So at the high level, this idea of building all these things on top of dissimilarity allowed us to make some high level predictions from the framework, predictions that we believe would be true independent of the domain. And I'll go through a couple of those. So the first was that novelties with greater dissimilarity will be easier to detect, but will be harder to react or adapt to such novelties. So it was a sort of two-part prediction. Things that are farther away in dissimilarity space will be easier to detect in some sense, because if I can approximate dissimilarity space, they'll be far away, therefore they'll be easier to detect, but it'll be harder to fix things because they're so far away. The second one was that imperceptible novelties will be difficult or impossible to detect. That's going to decrease agent performance and decrease the predictive power of the associated theories. And we'll see, we have some experiments that sort of validate some of these. The last one, which was something we were very worried about and has shown up in some of our experiments, is that nuisance novelties will present experimental difficulties for scoring. And theories that have lots of nuisance novelties will leave poor prediction of the novelty's impact on performance. So if I want to say, how much will this affect my system? If I have all these nuisance novelties, I'm going to have a very bad ability to predict that. Now, we've actually gone through experiments to validate almost all of these. Come on. Mouse. I lost my mouse. Here we go. This one has actually not been validated. We found it was true in some domains and not in others. And the reason for that is it actually depends a lot on how you adapt. So when we talk about some of, for example, of our open world novelties, it will be easy for us to adapt. If I take a faraway class, I can build a new class around it. There's nothing near it. It's easy. If I take a planning system that's working in a discrete space and the new world is very dissimilar, it may not have the operators to ever react or adapt to such novelties. And so it may not be able to plan. And that's why it's harder in some domains and not either others. So it will be domain dependent what's going to happen with that. We also made some other very high level predictions, which is when the dissimilarity weighs world or observed dimensions inconsistent with their impact on task performance, the dissimilarity will be a weaker predictor of novelty, detection, reaction, or adaptation. So now I'll go through an example where you sort of see this, but basically if my world, we had it as a d prime dimensional vector, if I weigh some of those dimensions in a way that isn't consistent with what happens on task performance, then we're gonna have a weaker performance. So this helps you get some ideas of how to do better designs. The second was that when the world and dissimilarity operators are inconsistent, it will actually often create imperceptible or faux novelties, reducing the predictive power, which is actually related to the first one, but actually more specific, because we actually say part of what we can go looking for is, does this create imperceptible or faux novelties? And we've been able to generate both of them. And then finally, when regret measures are inconsistent between the world observed and agent, or they weigh dimensions inconsistently on task performance, then there's going to be a lot of these nuisance novelties because one of them will be measuring something very different. And again, limiting our purpose. So these are actually sort of describing ways in which we predict you can make nuisance novelties exist or make faux novelties exist because of the way we play with how we weight dimensions in dissimilarity. And some of these are actually pretty easy to imagine. So if I imagine a world where I have a whole bunch of variables in the world and I throw many of them away before it's observed. So if I do cart poll, actually, I'll say that's when I get there. You'll sort of see where that comes up. Back over here. So one of the reasons I went down this path, and Walter and I were sort of some of the key instigators for this particular type of theory, is because we've already been thinking about things this way for a long time. Many of you may have already seen some of our work on extreme value machine-based detection and the basic EVT-based approach. But this theory is very consistent with the idea of EVT. So if we have this world dissimilarity operator that lives in the world, we can't do much about it. But with the observed dissimilarity operator, if I can treat that as a pseudo distance metric, then I can compute dissimilarity and measure distance to our extreme vectors, create the evaluate the viables, and take the match probability to get what's the probability of input being novel or not. And then if I want to do open world learning, I can sort of cluster those novel things and make new ones come up. So once we have theories, the framework devises a theory that is consistent in terms of dissimilarity operators, we can then directly start trying to apply our EVM approach, which is part of what we've been trying to do in this project. So we start with our feature training for whatever the domain is. The stuff in blue here is all going to be domain independent. Somebody does some feature extraction. We get the pairwise distances, we get the viables. We use our set cover to get our extreme vectors and reduce the set. When I want to add a class, basically, I find the nearest distances, find the nearest negatives, get new extreme vectors for the new classes and add them. So we can both do training and adding of classes. And then at test time, we just go through what I already said. We get the distances, we evaluate probability, we get our probability of unknown, and then we can get our either K+1 or K for Openset or K plus M+1 for open world probabilities. So when we're doing this, we're part of this large, as I said, large DARPA effort. One of the things they've done is they've separated us into what they call TA1s, the groups in charge of writing tests, and TA2s, which is what I am, which is in charge of trying to solve the test. So we have to handle the problem. So we actually had two different sets. I'm going to just talk about the one here, which is Openset image classification. So this particular set of experiments, we have two subtasks in this problem. So the first is we're going to have a K+1 classification, Openset. We have to say it's one of the known K classes or its background or whatever. The baseline agent is going to be a ResNet 50 trained as an Openset classifier with a background class using 5,000 known unknown images. And then we have some training data. And so University of Maryland was our partner on this. They're the TA1, they put this together. Our two tasks are actually twofold. The first one is to answer the question, when has the world changed? And I'll show you that in a second. And then the second is to do the Openset. So the when has the world changed is sort of interesting. When we've published our work on Openset, we sort of presume that we're now in a world where the Openset has happened, unknown things happen. But one of the things that came up in the Salem project was this slight change in what we wanted to do the problem. In the beginning, we're working in the known world. And then some point in time, these unknown things start showing up. So we were in the lab, everything was working fine, and now we go outdoors, right? If we go outdoors, we might know things are going to happen. But in general, if we're just getting a stream of data, we have to decide what we'll call when was the red button pushed and the world started changing. So during training and testing, there really are two different distributions, the training distribution and the test distribution, which includes unknown objects, Openset. But we don't actually know up front which of those we're going to see. And we have to detect when does this change happen, as well as being able to do the class detections. So this was sort of a new Openset related problem. Last year at WACV, we had a paper called Towards Open World Automatic Reliability Assessment. And the problem was, and I'll show you what we're trying to do down here. The reason this problem is difficult is that if I look at the scores for my known classes, so here's softmax probabilities on the left. Here's EVM class probabilities. So different ways you can think, if you want to think of just your raw softmaxes, and EVM probabilities. Now, some of these are from before the button was pushed, and some of these are from after the button was pushed. And I'm not going to tell you which is which. Which of these do you think are before and which is after? You'll notice this is not easy because the distribution of these is actually very similar. It's not obvious which ones are which. And so you have to look at that, and it doesn't matter if we do EVM or the softmax, right? The distributions are pretty close. So we came up with this idea of basically looking at the distributions. And the reason the distributions, we have to look at this as distribution, not per image, is you got to remember that our classifier, this was at the time, I think we were using a efficient net B3, maybe B0. But on ImageNet, any of these classifiers is only 70 to 80% accurate. What that means is 20% of the time they're wrong. And very often when they're wrong, what's going to happen is the system's going to say unknown. Because whatever you called this banana, right? It was supposed to be a banana, maybe it's a banana tree instead of a yellow banana. It gets it wrong, right? And so, but sometimes it'll say the wrong class, but other times it'll just say unknown. So lots of things get these scores that are sort of unknownish in terms of where they're going on. They have low softmax scores, or they have very low probability, max class probability, so high probability of unknownness. So what we do is we take these, we put them together into we use a Gaussian to represent the distribution, not the actual scores themselves. But now we're using sort of central limit theorem. We're looking at the representation of this distribution. And then we can compute batches. We get some mean and threshold and variance over that. And then when a new batch of data comes in, we start looking at that. We do this truncated Gaussian fitting and then compute the KL divergence to be able to say, can we do this? And this gives us some nice performance. So here we actually had another algorithm we had developed called OND, which actually follows the KL divergence pretty well. But if all we do is do KL divergence on softmax, our percentage of detection is much lower when we're dealing with a very small window size. When we get to really large windows, softmax actually starts to do a little bit better. So there's a trade-off in terms of where they're going. But one of the classic algorithms, which, if we just consider, for example, looking at the average of softmax and thresholding based on that, you're way down here. Your percentage of detection just really doesn't work. The percentage of unknowns is what's on the x-axis here. So as we increase the number of unknowns, the more unknowns that show up in my batch when the button gets pushed and the world finally changes, the easier the problem becomes. And for very small percentages, it's harder. But this KL divergence with the EVM scores worked out pretty well for now being able to decide this other open world problem. And again, this is going back to our key theory, which is now we have a dissimilarity measure, and we have a dissimilarity measure at the image level, but we also have a dissimilarity measure at the batch or at the group level. And given that, we can make things work out. So coming back to how this relates back to our generalized theory. So we have a world state that consists of object class labels and object attributes at every point through space. Yes.
Just one thing. Yeah, I was not able to see you.
Oh, I see. Yeah, I moved the camera to be able to see the last numbers on the plot. So sorry about that. So in our going back to our formalized framework, right? We have this world state. The world state to us is not something we as a TA2 ever get to see, but when we get scored, Maryland is going to use labels that came from humans, the attributes that came from humans. And those labels are all going to be top one. And we'd already said this, but sort of where we got stuck, where we were because of the way the program was going forward, right? Top one is going to create more nuisance novelties, which is going to impact our abilities. But the number of classes was smaller than all of ImageNet. And so it was maybe a little bit better. Our perceptual operator basically is an image. Our observed state is our image. The ideal dissimilarity is from the human labels, right? Better than that would be actual comparison of the image and say, is this label appropriate? But instead, we're actually going to use an approximation via DNN where the labels were used in learning and ground truth labels for test examples. So we can use the fact that we actually have a full ImageNet trained classifier, so that both the training and test data, right, are things that ImageNet would normally be able to classify, but they broke it up into subsets. Our observed regret is 0, 1, depending if the labels match, or novel if it's not from the training set. Our observed dissimilarity operator, which is the similarity on the images, is 1 minus the maximum confidence of the baseline classifier for known classes. So notice now we've gotten to a dissimilarity operator that's computational, but it's also a little bit biased because it depends on however they trained their baseline. But it still allows us from a novelty point of view to have a formalized definition we can use. As I said, actual human labels would be better, but that's just too expensive to run in a large scale experiment. Our regret is the number of misdetections for task 1, which is like when did the red button get pushed, which is 1 minus the number of correctly detected trials. And then for task 2, our relative performance and our regret is defined by 1 minus this, what they call the novelty response performance, which is a really bizarre measure I don't actually recommend, but it's what was put on us by the program, which is the performance in terms of classification accuracy of the predefined baseline system before novelty happens. And the top here is our system after novelty happens. So they're sort of saying, if I look at what happened with the baseline before any novelty was introduced and comparing that to our performance after novelty was introduced. And we expect after novelty, things will go down. And the question is how much? So by looking at this, and this is now data that came from the group in Maryland, because we don't get to know what the answers are. They run the experiments. They really had 3 different dimensionalities for how the observed distributional dissimilarity can be measured. So the first is how dissimilar are the selected samples, and that's using this per image classifier. The second, and that can be low, medium, or high, which correspond to the colors over here, low, medium, and high for blue, orange, and green. The percent novelty, percent of novel samples in the batches that we're going to see can be either small, medium, and large, which is within each of these images, I should be doing this, right? Low, high, and medium are these, the colored bars. Small, medium, and large are this overall left column versus the right column. This has less novelty data. This has more novelty data. And then distributional time shift, which is when did the novelty get introduced? Does it get introduced very early in the experiment, which means I will see a lot more novelty because I started early and then it sort of comes up over time? Or does it show up just at the very end? And now when I detect it, I only have a couple of trials where I might be able to see it, or a couple of batches. So all of these come together. And interestingly, if we look at this, we go back to our generalized framework high-level predictions. Our framework predictions would have said higher dissimilarity, image level novelty is harder to react to, which would say blue is greater than orange, is greater than green, right? And we actually see that in our domain. Higher distributional frequency, this is novelty reaction performance. Higher distributional frequency is higher dissimilarity. So left should be greater than middle, should be greater than right. So left has higher scores in general than the right. And distributional timing, bottom should be better than middle, should be better than top. And again, we see all those. So this experiment was very consistent with our framework level predictions of what we would expect to see. When we look at task 1, which is the detection, percent of correctly detected trials, we would expect that higher dissimilarity is easier to detect. Blue is less than orange, is less than green, and it's a little bit true, but not completely. Higher distributional frequency, left is great, is better, is worse than middle, is less than better than right. A little bit true. This is definitely the worst column. And then timing, bottom is worse than middle, is worse than top. And again, this is definitely the worst. So generally consistent, but not completely consistent. So in doing these experiments, now I'm going to step back and look at the architectures we use and talk a little bit more about Openset. But I wanted to stop at this point and sort of ask any questions about this aspect of this sort of the generalized framework, how we reduce that to a particular task, and then the sort of experiments and predictions we saw. Can we have a way of saying, what do we expect novelty will do in our problem? Any questions?
Folks, if you have any questions, you can type or open your mic, or if you prefer, we can have questions at the end. It's up to you.
I can definitely, I'll take the questions at the end as well. I just, sometimes when a longer talk happens, it's easier to remember them while they're still fresh. So any questions showing up? If not, I'll go on.
No questions, sir. Please go on.
Okay. So as I sort of said, we earlier had this idea of Openset. And so this is the underlying this is sort of how we're using EVM. So the Openset version is straightforward. We have feature extraction followed by the EVM, followed by change detection, where we decide whether or not the button was pushed. That's the KL algorithm I mentioned. Then we decide, is it novel or not at an instance level? And we may or may not adapt our threshold, which went into that. And then we actually at the end give them a novelty characterization. Here's all the things we thought were novel. The data I showed you was really just looking at two very simple tests, which is what's our reaction performance with that weird measure, and then what was our detection performance. We also in this project worked on open world, and we'll come back to it's a lot more difficult to evaluate in the open world. But the idea was actually pretty much the same. The open world, the difference between the open world and the Openset algorithm is here, after we've done that novelty classification, and maybe we've done this change detection, so we can turn this module on or off, we start doing novelty characterization with clustering. And then given we've clustered something, now I can add new classes and do full open world, right? But again, the way we've implemented the system, all of both the Openset and the open world parts were done in a way that is domain independent. They don't know anything about the fact that these are images. All they know is they get a feature vector, which could have come from images, from video, from documents, and any of those, when they come in, produce in general, a deep feature vector that we then do this processing on. And I'll come back to some of that in a little bit. So one of the things we did, and we have an archive paper, there's no archive link on it. Oh, maybe the next page I'll get to it. We've been looking at a particular problem. Now, the one thing that we got in this effort was they don't want to tell us what is novel. And they don't want to tell us the labels of anything. So all of the prior work our lab has done on Openset and open world learning, after we decided something was unknown, we could go to some human and say, what is the label? Really, we just went to a data set and pulled out the labels and we use them. But here they were challenging us to look at the problem. What happens if you don't get labels? So we formalized the open world learning without labels problem. We sort of defined a new metric to measure the quality, because in the open world without labels, I can't actually ask what's accuracy because I don't have labels, but I can look at some clustering metrics. And even after the fact, after you give me labels, I have this problem. I might have taken a class and I might have broken it up into two pieces. And so which of those do I say is the accurate one? So by using this B cubed measure, we can get something that does a slightly better job. And so we did, not with the data from Maryland, because we don't know what their answers are. We did our own experiments with 1,000 classes from ImageNet, plus 166 classes from ImageNet 2010 that don't overlap with the ImageNet 2012 data. And then we did our algorithm with EVM clustering and incremental EVM to allow us to incrementally load the classes. And we actually did two very interesting parts in this part of our work. We looked at what happens first. How much do we get if we get the supervised label? So this top line here is supervised features in the beginning. When Openset happens, our performance drops. And then once you start allowing me to adapt the system, so it's open world, with supervised features, we climb back up. And after 80 batches, we're actually pretty close to where we started. It starts over here in the red line. But because we're now dealing with some of the issues we know with Openset, we wanted to also look at what happens if we use self-supervised features. So in this legend here, S means supervised features, I means ImageNet self-trained, self-supervised features from ImageNet. I think they're MoCo v2. And then this is with places, which is now a different data set, right? So here we're using self-supervised features from the same 1,000 classes of ImageNet, and giving us the yellow. And then the purple is with places. And then here, all these three get labels. And I'll come back to those in a second. Then we have them where they're getting just unlabeled data. So this red line here is supervised features. Open world happens, their feature performance drops, and then it only climbs a little bit because with unsupervised features, it really can't do much. On the other hand, these bottom ones are what happens when I start combining features. So this is initially supervised features plus ImageNet self-trained features plus Places self-trained features. And you can sort of see by using these self-supervised features, even in the closed set, we got a boost in performance. We maintain that boost, but not by as much in Openset. And then in the space where we're doing open world learning, it outperforms supervised features again by around as much as it did in the closed set. So it was able to maintain its performance. And it pretty quickly jumped up from the open set to the open world with much better performance. And doesn't learn a whole lot after that, but it does a little bit better in the beginning. On the other hand, if I look at these pure single classes of features, right down here, they all start with just self-supervised features with no supervised data. Performance is much lower, it drops down. But interestingly, when we start playing in the open world, it actually increases more. It doesn't quite get to the supervised performance, but this sort of performance afterwards climbs up. So a couple of interesting observations were that we can do this open world learning without labels, and that unsupervised features helped us in terms of increasing our performance. It did better than just supervised features. And at a certain level, this isn't terribly surprising because supervised features have a problem. They sort of fold over each other when you get unknowns, and so they don't work out as well. So as I said, that's an archive paper. And we've been working on this, but as we've analyzed it post that first version of the paper, we're working on a new version to submit to a journal. One of the things we found is that first there was a lot of variation among the random tests, but we started looking at what do we get for answers as humans. So these are some of the classes that we got by doing this. And in the base classes, there weren't these trees. And what's sort of interesting is when we started analyzing this, here's a cluster, here's a cluster, this is a cluster. But one of the problems that we found was that very often the visual clusters, and when we show these to people, these all look like pretty good clusters. The problem is the true labels are white birch tree, which is what this kind of tree is, gray birch tree, which is what this tree is, yellow birch tree, which is what this one is. So there's 3 or 4 kinds of birch trees. This is also another kind of birch tree. Same is true up here. Same is true some of these other fruit. What it ended up doing was clustering based on visual similarity, but tree trunks and tree flowers and tree leaves, right, don't necessarily look the same. And trees far away and trees up close, they all look different. So we are now working towards a more difficult problem. If I'm going to try and learn without labels, it's not even clear how to score them. Because if you didn't tell me you cared about the type of tree versus how the image of the tree looks, is this a better classification than if I put the birch trees in separate classes? So some very interesting questions as we continue down the open set and the open world, where what labels mean for us to learn is an interesting ongoing research question. So we're working on a new paper that's not completely going to address this. We won't have it in time for this year, but because now we have to go back and get lots of human annotations to score this. But as I said, when we designed this theory, we really wanted to make sure this was not just for images, because the goal is a much broader theory. So we actually have some examples now we're going to talk about from a simple problem. This is a 2D version of cart pole. We have a cart and it's got a pole on top of it, and your goal is to balance this cart. It's a control problem. And actually, you only have 3 choices: do nothing, move left, or move right. You don't get a choice of the force. You don't get, you just move left or move right. So a very simple, very straightforward problem. The world state in this case actually has 16 dimensions, which are these variables here. But the observed state, going back to our model, only has the last 4 of these, which is the cart position, velocity, pole angle, and angular velocity. We don't get to know the force of the push, the mass, or any of these other things, or even gravity. And so when the world becomes novel, it might be that somewhere along the way, the mass of the cart changes, and now we have to detect it. And in the beginning, the easiest way people were looking at this was looking at a simple dissimilarity measure, something like the Euclidean distance between world states. And if I do that, what do you think might happen? Based on the theory we've talked about, do you think Euclidean distances will be good? Is a change of 1 unit of pole length the same as 1 unit of min-max cart pole position, or 1 unit of cart mass? Probably not. We said in our theory we'd have some problems. So if we actually look, and this is with a DQN agent from Larry Holder's group at Washington State, so this is work he did. He sort of looked at what happens as I vary gravity, and I can look at the normalized dissimilarity among different world states where I've been playing with gravity, and then look at the normalized performance of the system. And while overall, as I change gravity, there's a linear trend, this data is very disparate. The same was true with force. If I vary force and look at normalized dissimilarity, the normalized performance, a little steeper curve here, but again, there's a whole bunch of points down here that it's not just this effective force. So when I change force and other variables change, right, all kinds of things can happen. Pole length, similar, right? So the problem that was as predicted, using Euclidean distance between world states and observed states was dissimilarity as a dissimilarity measure was a very weak predictor. It depends on the units. And literally, if I change things from millimeters to meters, right, I multiply some dimension by 100 or divide it by 100, right? It also depends on the starting dimensions, what dimensions exist. As I said, imagine that there are dimensions that would have some. So if I added color, right, it doesn't matter if the card's blue or green or yellow. It doesn't change how I balance it. And so that dimension all instantly causes me problems, because if I use that in measuring dissimilarity, I'm going to break my task because I can change it to whatever I want. And it's not going to change my task at all. This is why we said having these dissimilarity measures. So the group started looking at this and how they're going to develop their measures. And Shemik from UMass did a really nice job where he really compares two worlds by asking the question, if I start from one of them, can I get to using a small agent? So now I have to have some agent I'm going to use. Can I get from the first world to the second world and look at how different they are? And then we can actually normalize that by averaging over all these states, including in the initial observed state. And he gets this observed dissimilarity measure. And when he looks at that dissimilarity measure and how well it predicts, so if I have the agent's forces and the world's forces, and I look at the correlation between, the brightness here is actually now, excuse me, the expected results in the world state, we now get these very correlated results. But it's not actually true for everything. If I look at gravity over here and I look at the change in gravity, right, now the performance is not so good. And this is really because it turns out that the agent doesn't really, unless the gravity is too little or too big, it really has almost no impact on performance. And then there's other variables, like if I have a sort of wind pushing my cart, then they become, again, correlated and you can relate the two of them. So a lot will depend on which variables you look at and you want to change and play this game. We went back to our model and we just defined dissimilarity slightly differently than Shemik did. We looked at the observed state as a sort of temporal pair. And then we looked at the dissimilarity as the distance vector between the states and the simulations that we'd already run. So we sort of imagine we run this offline, we get some simulations. And now we can look at differences between states we expected and what we see. With that, we can train our EVM using the normal plus some hypothetical small perturbations to get a feel for what's going to happen. And then at test time, we feed this into our EVM KL world change predictor and the per instance novelty detector. And our control algorithm is just trying to keep the simulated difference as small as possible. And sort of the plots you see going over here, which are sort of a sequence of different images. This is the normalized performance. Again, it's the same sort of normalized performance. His state-of-the-art baseline image algorithm divided by ours. You'll see that most of the time our algorithm does much better. We're at the top, and sometimes we'll drop down a little bit. But while lots of the things are impacted by novelty, our algorithm is much less impacted by novelty, and the discrepancy actually is not easily predicted. This is why I said we saw the example where the things that have large dissimilarity are not necessarily hard to deal with. In this case, some of them were easy and some of them were hard, so we lost that. Our prediction performance, I don't have a plot because the software basically said it was perfect performance. We predicted every one of them, so we have nothing to show. But this was really to show that we could take our EVM-based approach and we could apply it to the problem of novelty detection now for something is nothing like images. All we get are these four variables: cart position, cart velocity, pole position, and pole angular velocity. And those are the four variables we see. The world has changed in the other 12 dimensions. We don't get to know which ones, and we're still able to use EVM and our KL-based EVM detector, both to detect changes and to drive our simulations. Another example we did, which is actually outside of the project, but we had also been doing this, was looking at intrusion detection and image classification. The image classification, ImageNet, so it's pretty much the same. But this is an extended algorithm from another one of my students, James Henry Doss, who graduated last year, looking at this. And we basically took our EVM approach and we built a new algorithm called CEVM, which is clustering enabled EVM. And this was done for two reasons. One, it allows us to reduce the amount of data So it's a lot like the original EVM. In the original EVM, I take a point, I find all of its nearest neighbors, I fit a variable to it, and then I take all of those points and I figure out who covers who. In this case, we first take the data of the classes and we cluster them using some clustering algorithm, in this case, dbScan. And then we just take the centroids of those clusters. So if on average, every cluster has, say, 100 points, now I reduce my data by a factor of 100. And then I go do the same EVM algorithm on top of it. So I basically have this first data reduction stage. The data reduction does two things. It reduces the data, which can make things a lot faster, but it actually also has the advantage of sort of getting rid of some noise. When I cluster points in very high dimensional space, some of the dimensions that matter a lot will continue to have separation, but dimensions where there is noise but not much meaningful things will collapse down and will become easier to deal with. So with this, we were then able to use the CEVM algorithm on both KDD intrusion detection and on ImageNet. And here we sort of spent on F1 measure for the difference between the CEVM and the regular EVM. And on this data, EVM was already better than a number of other algorithms, so I'm not showing all of them. And the same was true here for the KDD data. We got a noticeable improvement with the CEVM, and we actually looked at a couple of different performance algorithms. We looked at both dbScan and HDBScan. It didn't really make much difference. So relatively stable performance. So again, showing something completely different kinds of data. It's not integrated for our Salem project, but very different tasks, but still the same underlying idea. We defined a similarity in measures in this, and then put EVMs on top of it. The last example was some work by Walter Shire and his students at Notre Dame. So it's not really my work, Notre Dame. They basically were looking at writer identification. So given some handwritten transcriptions, you want to both figure out exactly what the words say. So do the transcription problem, but also be able to say who the writer was. And they had a paper earlier this year at I said here it says ICHCAI. It's actually ICDAR. Sorry, my bad. But they had this nice set of data, and again, use exactly the framework. They took the novelty definitions, derived it, but in this case, they ended up using our EVM with some interesting twists on top of it. They weren't using deep features. The features they used were actually standard, I think, hog features. So it's not all tied to deep features. Wanted to show the examples also work outside of that, although it's not our work. So sort of ending the conclusion side of this, we have this new unified framework for theories of novelty to support your work in open world, out of distribution, anomaly, whatever you want to do. And the nice thing about this is it allows us to be more precise about defining what is in the world, what is in the observed, what is in your algorithm, right? And talk about the novelties between them. We've demonstrated this allows us to make predictions at both the framework level as well as the instantiated theories. And the process of formalizing your novelty problem may provide some new insights. It did for us in both the image domain as well as in the discrete domain. We have a couple other things I didn't talk about here because the papers are not yet out on other ideas that came to us because we were working at it and looking at it this way. So that formalization can actually help you. So now we're at the end. I'll take some questions and reminding you again that we have postdoc opening while we talk about questions.
Thanks a lot, Terry. Very nice work. I confess that I hadn't thought about like novelties as completely as you did. Like for me, novelty was like it's there, it's not following the overall distribution, so it's novel. But you showed that we have several other vantage points to consider. So
which distribution? The agent's distribution, the observed distribution, the world's distribution. Exactly. In fact, I'll add another one which we're working on. We have a paper. I think we have a paper on arXiv now, where one of the other ones we're really struggling with is if I've seen an image and I haven't seen its label, is it in my distribution or is it not in my distribution? It's in the distribution of images. I've seen this class, but I didn't know it was a giraffe. Right? So I don't have a label. So which distribution, even for the observed space, am I observing image and label or just image, right? And again, another variation we've not actually well formalized in the literature in terms of which of those is out of distribution.
This goes exactly in the direction of my first question to you. So one important thing that we have seen in literature recently is the self-supervised learning. So you start completely unsupervised, and then you can do some initial grouping, you propose some pseudo labels, and then you keep like a feedback loop trying to work on that. So how do you see your theory fitting in this self-supervised learning with a feedback loop that you try to compose new groups on the fly?
Yeah, so we actually have done this. We have like 3 or 4 different ways we've been approaching it. So the first, as I said, is we actually have to have a formal separation of what we call now out of distribution versus out of label, right? Because so self-supervised is in one sense out of label, right? I've seen the images, but I can actually have self-supervised in this example, right? We have self-supervised on ImageNet. That is out of label, but I've seen the images, right? But I haven't, so sorry, this is actually the same label space as supervised. So just seeing the images, but not seeing the labels of the same data didn't help so much, right? It's way down here compared to the supervised labels. And this is MoCA, which is one of the near state of the art. But when I combined, if I go down here and I look at I plus P, right, ImageNet plus places, right? Here's places, here's ImageNet plus places, right? And just ImageNet is cyan, right? So adding this didn't actually help much. But as soon as I add a little bit of supervised data, my performance jumps up a lot, right? So it's the answer to like, what are we doing? We're exploring it because it's really complicated, but also unknown. Sometimes they're helping a lot and sometimes they're not helping much at all. And I think part of the answer to that has to do with in my feature space, once I have, and I'll say, we've done some things with smaller sets of data and you get very different answers. And so for all of those who are thinking about doing Openset work, Openset, and this is one of the talks I gave over the summer, like at the Open World Workshop, right? Openset, when you're playing with 10 classes, isn't really meaningful, right? Because what happened is you so limited your space. And maybe there are problems for which it's meaningful, but especially when I start playing with feature spaces and learning feature spaces, 10 classes just isn't enough to learn a really meaningful feature space. And so I'm really playing this very weird game. Once we get to ImageNet, where we have 1,000 classes or places where we have, a million images, right? The feature spaces become pretty good. Whether or not they're self-supervised or supervised, we can actually get a pretty big difference. But the place where I think that this distinction between self-supervised and not makes a bigger difference, and it's not in this plot, but there's a number of people who are doing self-supervision on the test data. So like Auto Novel as a paper went out and they basically trained their feature set on both the training and the test data, self-supervised. So in a sense, they're sort of saying, it's okay that I've seen the test data because I didn't see its labels, right? And that may or may not be an interesting paradigm because now my feature space is only out of label, including all the test data, and I just haven't learned the labels. But I may have, in a self-supervised way, learned to separate those unknown things, which is different from if I just train on the training data and I've never seen a giraffe, and now I have to deal with a giraffe. My feature space, and we had a paper at NERPS in 2018 on we called Reducing Network and Exophobia, where we sort of showed that even these small dimensional spaces, unknown objects map directly on top of objects, known objects. So unknowns will just map on top. And once they're in feature space and on top, there's not much you can do, right? Because now they're in feature space exactly the same as the things you know. And I think that's where there's still some interesting potential. And for some problems, for example, robots, right? Or maybe little kids, right? Seeing the answers, seeing the test cases without labels can be meaningful, right? I can wander my world and see all this stuff and then only later ask what the label is. Babies have learned almost all of the visual features in their neighborhood before they ever can get a label.
Excellent. Terry, my student Gabriel is asking something interesting here. And then we have Pedro. So Gabriel is asking if you had thought about using explainable AI techniques or some sort of those techniques that can explain something in order to know which parts of the images are highlighted after self-supervised learning. Do not the image activations help to infer a possible label of images? I mean, if the model put all the images together, the activation regions might help to justify why they were grouped together. So he's trying to ask something like, with the theory that you proposed and the methods that you have to detect novelty and propose new groups, do you have anything that you explored in terms of explainability to help you in that feedback loop?
No, I don't think that anything in neural nets are explainable. At a deeper level, that's a whole different talk. But the work I've done on adversarial attacks on the deep networks suggests to me that figuring out where the activations are happening isn't really an explanation. It's just sort of saying they're active here and we don't know why, right? And so when I think of unknowns is a weak kind of attack, because where they end up in the network is part of the question. If they map on top of known things, we're going to get them wrong, right? So the activations may look exactly like a known image. So the other reason is I just have finite bandwidth. So if Gabriel wants to go down that path, there might be something, I'm sure, because you can make nice, pretty pictures, I'm sure you can make a nice paper out of it and give an explanation that will make some people feel this explains some of what's going on. But at a deeper level, none of those techniques explain adversarial images. And so I worry that the techniques don't generalize well enough. Right.
Another thing that when I saw your papers, two things actually. How do you see these applicable to just domain shift? I mean, you have the same set of classes, but something weird happened in the tests, and you will have the same test, but with a different distribution. So do you see some application there?
So, well, applications so I'll come back to the application first. Will this idea work? Yes. So when we talk about dissimilarity with this model, it easily handles domain shifts, because now if your dissimilarity model can measure shifts in the distribution. So when we did the KL divergence, we actually did a very simple Gaussian, because we simply said scores for knowns and unknowns. If we had done and we need more data because our batches are very small, like 32 or 50 or 100, right? You can't build a very large Gaussian. But if I did one that looked at the probabilities of different classes, right, then I could be looking at domain shift and starting to say the same question: has my probability of the distribution of classes started shifting? So the same idea would apply, just would need a lot more data.
Right.
The applications of that, right? So detecting that there's been an increase in something, there's absolute. I mean, so my surveillance companies, right? That's a big part of what we had to do. But we also have to be very careful, because domain shifts, you have to be very careful to talk about the time period, right? Yeah. So my company, when we worked on that problem, had to worry about literally year-long cycles, because what I see in March looks a lot like last March, but not very much like what I see in June. Right. So the domain has a shift, but also might have a periodicity to it. So I got to think of it as a broader distribution or as a time index and distribution, and then work through that. But being able to detect it, this dissimilarity, I think, would still apply.
Okay. Thank you. Pedro, please unmute and go ahead.
Hi, Terry. Thank you for the talk and for coming here again. I have a kind of two questions that is mixed regarding this different uncertainty, novelty definition, sorry. You define there the word, the observer, and the agent one, right? And and the dissimilarity is all on the word space, right? This word space, what you call this word space? This is the raw input sensor, or would be, or you are assuming kind of the space of a feature vector that is defined somehow?
So that, I mean, that's a really good question. In the first version of the paper, we did not define observed dissimilarity and agent dissimilarity. We defined them in their own spaces. Observe was an observed space. But as I said, one of the problems we ran into is that the perceptual operator, right? We don't actually show where did it come from? And if the perceptual operator, for example, depends on where the robot is actually happens to be in world space. And so if the robot thinks it's, position 1, but actually it's in position 1.5, right? So its estimation of where it is, well, that then affects the the perceptual operator. And so we left the definitions of dissimilarity so that a oracle, because these dissimilarity operators can live at the oracle level, they're above the agent. And then at the agent level, we left them with world, even though the agent, we're defining agent dissimilarity, we left the world because whether or not the agent thinks it's in a novel state, which is part of its dissimilarity operator, right, can all be done entirely in its state. But in the example I showed where Shemek in the cart poll, he ran this sort of averaged over stuff. To get to the variables he needed to define that, it needed to be in dissimilarity space because you're averaging over a whole bunch of runs of the world. And so we left those definitions general so that people who use the framework could make it smaller. In the examples we gave for image classification, our observed dissimilarity operator lived in observable space, right? I wanted something where I could compute it, and so far I can't ask about the world. But when you live in a simulated world, which a bunch of the people in this project live in, if you live in a world where everything is known or knowable, then you can ask those questions about the world, even if the agent can't. The sort of evaluator can, and so it left that broader definition available to them.
Okay.
Does that answer your question, Pedro?
Yeah, kind of. Yeah. Maybe I'll check what's the difference between among those words. But the related question I had is regarding the experiments you did show. How did, because I understand these these different definitions of novelties is good for understanding the problem and having a more fine-grained view of the problem. But how it did happen on the to help solving the problem, Openset, open world problem.
So it helped first in two ways. By having this and having these discussions, first we were able to better design experiments, right? Which is actually an important thing. If I want to have a good experiment, I have to think about how am I going to measure that? And so it helped with the design of the experiments so that we could, one of the goals was to sort of be able to have this variations where we have easy, medium, and hard, right? And in fact, in this case, we have easy, medium, and hard in 3 different directions. Because we could make predictions, right? We could they could separate their data, right? Based on what they thought were easy, medium, and hard at the image level, but then also in ways that we talked about the distributional aspects and design their experiments. And this gave the ability to have experiments that gave us a deeper understanding of how the systems perform. And this is just one system. Actually, other systems went through the same evaluation, and some systems were better at detection, some were better at response. And so there's a trade-off across this space. The second way it helped is, as I suggested, we'd actually made these predictions that these things, right, would be, these kinds of things would be problematic, right? This whole idea of nuisance novelty. And this is something we have continued to struggle with in the program. And so some of the things we did in designing both the experiments, but also in designing the evaluation. So now the data sets were fixed, but when evaluating, if, for example, we didn't use multi-label stuff, but if we defined the agama here, right, but we had said it's a lizard, right, instead of an agama, which is a super class of lizard, are we right or wrong, right? So now it's like, how do I measure, is that right or wrong in the right space? And it's tough enough to say that, cherry is the right answer, not dog, but here, I actually got the right answer. It's this lizard, but there's not enough detail to really know for sure it's an agama, right? Maybe it's a horned toad lizard. So you might have said it's the higher level class. So they also had a way of scoring things to make that different. How does it affect our algorithms was actually more minor, because at the extreme value machine level, right, we just took the labels they gave us and we trained on them, right? But that gave us the ability. So in scoring, if we chose a subclass instead of a superclass, it wasn't a problem. The data set was a little bit different than the traditional ImageNet because some of the classes were intentionally super classes of others. So we would see a novel lizard. Maybe a gamma
Sure.
was the novel lizard, right?
But in that case, isn't it a limitation of the way that people annotate and try to solve the problem? I mean, if you create the recognition system to consider multiple labels at once, perhaps this could help you, right?
Oh, it could, yes. We've been talking about those problems, but this is, in a problem, in an Openset problem, right? They can say, no, this is the answer we want you to have. So top one for ImageNet is just a bad idea because too many of the images are like these, where there could easily be two. But programmatically, right? So I think eventually we convinced them. I think they ended up doing top 3. We didn't do top 5. We did top 3. Most of the images don't actually have 5 objects, so there's a trade-off. But Pedro's question about how we design our system, it allowed us to say we don't have to worry about making that extremely hard decision. Is it novel or is it a subclass of lizard, right? We could just say it's novel and not worry, oh, we have to decide, no, it's actually a lizard. We ignored the subclass problem, which is a kind of novelty problem that we, according to the theory, told us that's nearly impossible, right? It's going to be a nuisance because most people wouldn't say a gamma. They're just going to say lizard.
Mm-hmm. I have now Gabriel.
Hi, Professor Terry. Thank you very much for presentation. And can you hear me?
Yes.
Okay. And my second question, I did the first one about the XAI. And the second question here is about the ensembles, or in your case, a multi-agent system. What if we test the model with more than one agent? What I mean, and how can we combine multiple answers from multiple agents? The first agent say that's novelty. The second agent say that is a novel case. The third agent say that it's not a novel case. Have you ever tried something related to this, to ensembles or some strategy taking answers together?
Yes and no. So first I'll start with what does the theory tell us, right? So in our formal definitions, we would treat an ensemble as a thing, an agent, right? How the agent gets its answer is up to the agent. So if they take, board accounts, or if they take majority vote, or if they take sum scoring, right? They do something over many instances to decide whether or not it's novel, right? So at a theory level, that doesn't change what this function is, right? The function says, given inputs, we decide is it novel or not. So it doesn't actually have to change from a theory point of view to handle ensembles, because you have to have an ensemble plus a decision mechanism to deploy an ensemble. Right? So you have to have it. It is a little bit more interesting if you think of the ensembles, and we have not in any of the work we've been doing, but looking at the ensembles as having different views of the world. Right? So there's really two kinds of ensembles. Ensembles where everybody gets the same input, and then ensembles which are a distributed collection of robots that are each getting different inputs.
Exactly. This is what
that's a more
try to do.
complicated problem. Right? If you try and do that and you don't let the agents share, right? Now you get to a more complicated definition of what is their experience, right? Because each of them has their own little experience, and their perceptual operator doesn't get share, right? That would actually mess this up. When we first defined this, the first rounds of definitions, we were far more general. Everything were functions. They didn't live in RN. They lived in functional spaces. And we assumed there were operators to share information. It was just too complicated. It was just too messy. So we simplified stuff. Even now, people say it's too complicated. So there's a trade-off. So the only thing we've done with ensembles is with respect to within our feature space, right? We can take the observed data, and then we've done a little bit with different networks. So what happens if I do a ResNet 50 and a
VGG, or
we do a couple of different networks, combine those. But then again, we combine those and we put them together. And when I did all the work on supervised and unsupervised feature spaces, right? That's another kind of ensemble, right? Because we have features going in that are from completely different spaces, and then we combine them in a decision process. Most of our decision processes have been, and I'm going to say something that is because we're among friends, right? All of our stuff has been EVMs because that's what we told DARPA we're going to use. One of my students, Akshay, is finishing up his thesis, and he's actually saying, for a whole lot of these things, straight up softmax beats EVM if I measure accuracy, right? And for those of you who have looked in the Openset space, right, lots of our papers focus on F measure, not on accuracy. But DARPA focuses on accuracy, right? So that's why it becomes a more difficult question. Accuracy is not as good a measure when the data sets are imbalanced as F measure.
Yep.
And when we're playing with these, they're imbalanced. So in a sense, when we look at F measure, we're often playing this game of saying what's more important than not. So the other issue for ensembles is ensembles gives you more flexibility for choosing where in that space you want to be, not for a single measure, but if I really want to be at one end of the spectrum or the other, I can do some very interesting things with ensembles. So
Yep.
for a real problem, they can be very practical because one element of your ensemble might be very good at low false accept rates. The other might be very good at true positives, but terrible. When you go to put them
We are
together,
exploring exactly those things, and Gabriel here is doing some nice work on that. We have now some interesting results that put unsupervised learning quite on pair with supervised learning if the ensemble is well applied. So it's nice. We are gonna take a look at the things that you presented here. Perhaps we come back to you with some ideas.
some questions. Yeah, so that's fine. And as I said, we have a couple of archive papers on some of this stuff, and others we're still working on. We want to find a balance. The one thing I would say, however, especially if you're playing with ensembles, but for those of you who are being tempted looking at the literature on Openset, please don't do AU anything. Area under the curve is not how systems operate. But unfortunately, lots of the papers in the space have started doing AU, ROC, AUPR. Those are just not really good measures. Measure false accepted, or, measure points on the ROC curve is fine, but averaging over them, right? And you'll see this especially in the ensemble space, right? One piece of the ensemble might be good over here, and one piece might be good over there. And what I don't really want to do is say, I'm going to make an ensemble that just sort of mixes them. If I'm over here, use this part of the ensemble. If I'm over here, use that part.
Exactly.
Don't pretend that I have to mix them together to get good results.
Two last questions, one from Juliano and the other from myself. So Juliano is asking, have you applied this framework to something where these dissimilarities are not being measured between different points in time, but between different agents? For instance, two cameras looking at the same scene. Could you give some comments about that?
Okay, so I'll answer the first part. Have we? No. Can we? Yes. So the dissimilarity operator, so in a different level, I'm not even sure, maybe the answer is yes, because when we apply the images in our ImageNet style, right, there were, as I said, there were really two different problems we looked at. Bring it forward. One was, when did the world change, right? So if I were trying to decide when did it change, it's absolutely in time, right? And here we're using batches of data put together in time to decide that answer. But in these examples, all we're really looking at is an image, and we're saying what class is it, right? So here the dissimilarity has nothing to do with time. It's just really to do with an image and the training data. Now, pairwise dissimilarity in terms of a pair of images, right, could be defined, but now it's a question of what does that mean, right? So am I trying to say this is a novel stereo pair? I've never seen the thing this is looking at, or am I trying to decide that the disparity is out of what I've seen? So I've only looked at things far away, and all of a sudden I got a very close up disparity, and it's so you'd have to be more careful to decide what you mean by two images. But I can come up with many definitions. So if you define what the task is, I'm happy to chat a little bit about that, offline.
Right. Okay. So final question, Terry, like more of a provocateur. I've been working on some of these with you for some time, and it's always interesting that we always criticize the presence of a threshold, but you defined all the theory here based on the threshold, and we know that sometimes it might be difficult to find those thresholds. So do you see any way out of not needing thresholds to define this and go forward without them?
No. I tried very hard. So I want to be careful here, because the threshold is in the definition, right? So, am I the same person I was yesterday? No, yes, right? It depends on what you want to measure about me and how different with respect to that measurement. So this is a definition for the task level. how much of a difference matters, to me, has to be there. Now, so in the way we've defined it, it's a binary threshold.
Right.
In the first version, it was not. It was a penalty, right? But then you get into sort of like, well, it's a little bit novel versus it's very novel. That just made things more complex, and it didn't. We wanted some nice crisp definitions. So if you want crisp definitions, you need a threshold. If you don't want crisp definitions, you don't. But then we're still struggling to get our community to be able to do it in such a way that we're agreeing on what thresholds are, or sorry, not what thresholds, what novelty is, right? As I said, so we have about 20 different research groups working together. Only slightly more than half of them believe this is how we define novelty. So let me briefly answer, and then I'll answer Gabriel's question, right? Can it be an adaptive threshold? Yes and no, right? So in our world, it is. In some of theirs, it's not. And actually, in some of their worlds, I guess it is. We'll come back. A number of the groups define novelty entirely by it is out of the expectation of the agent. So if the agent has seen all the data, right, some set of data, and then the agent says that's outside of my model of the data, then they call it novel. And my problem with that is if I have a really bad model,
everything is outlier.
It's like, I believe that everything has the value 0. That's my model of the world, right? So if I wanted to find the definition of novelty based on adaptive thresholds in my data, I sort of could, but now I get into slippery slope. What's the model of the data that I have to presume? And again, if you go back to the dissimilarity measure, you can say there is a dissimilarity measure, and I compute that over the data. So in this example here, right, we computed it as the confidence over a baseline classifier. That actually is a number, and obviously it's a confidence number. So it's not, right? Dissimilarity here is a continuous number. You can apply whatever threshold you want. You could make it an adaptive threshold by saying, I have some validation task. And from that validation task, I compute this threshold and then I apply it. So can we do that, Gabriel? Absolutely.
Very good. Terry, thank you very much once again for your time. Please say hello to Ginger. It's always very good to talk to you. And everybody in the audience, thank you for your presence as well.
Okay, thank you, everybody.
Thank you,
and again,
Terry.
if you're
Thank you,
looking for
guys.
a postdoc, right. Okay, bye.
Bye-bye. Thank you.
Thanks.